Okay, so let's do an example problem with a self-tuning controller. So we have mx double dot equals u, okay? We're going to derive the controller just like we always have. We were going to say that u is m gamma, or I think they use v, okay? Except this is going to be m hat, and then v is going to be x double dot command minus kd x dot minus x dot command minus kp x dot minus x minus x command, okay? And this is my control log. There's no model, there's just a commanded input. That command could easily be a reference, but for now, I'm just gonna leave it. This controller is not adaptive in the sense that we're not gonna create m hat dot is not going to exist. This is not what we're going to do. What we want to do is we just want to estimate m hat. How do we do that? Well, the easiest way to do it, if you look at this equation, is to just say that m hat is just u divided by x double dot. Okay? If you measure the control input, here's the thing, this u is here, right? So if you just measure this signal, right? Measure this signal. And if you're flying a quadcopter or an aircraft, you're the one sending that signal, so you have that signal. It's coming from the computer, it's coming from the autopilot. You have that control input. And then here, you would just, if this is acceleration, you would just need an accelerometer. Okay? Now there is a problem with this estimator, and the problem is that it's going to be super prone to noise. First off, if x double dot, so let's talk about problems. If x double dot equals 0, m hat shoots to infinity and your entire thing blows up. If you take infinity and throw it into this, your control input is going to shoot up. You're immediately going to go unstable. Okay? The other problem is that x double dot is super noisy. So the problem is that if you just take one data point, like say u and x double dot, and you use that as m hat, right? You're going to get a huge, if you plot, m hat as a function of time, it's going to bounce around like crazy. The better idea would be to filter this, right? So take this value and just send it through some complementary filter. That's an idea. Your book has a better idea. And your book says, I would rather estimate it like this, where m hat is the integral of x double dot u dr over dt. I don't know why do they use r? I'm just going to use dt. I see what they're doing. I'm going to call this t final, and this is dt. So I'm integrating with respect to time to some final time, right? And then I'm going to do divided by the integral t final x double dot squared dt. Okay? So if you look at this, right, this is basically x double dot squared is on the bottom, and x double dot is here, so those x double dots cancel, and you're just going to get u over x double dot. The reason why they like this is because this is sort of a time average. So all of this noise is going to average out over time, right? And so that's pretty nice. So it's kind of like a filter in a way because you're integrating that over time. And the x squared, what the x squared does is that you always get a positive number, because if you get positive and negative, you're going to start to get zero crossings, and it's totally possible that this could still get pretty close to zero, which would drive your solution up to infinity. But if you do x squared, you're guaranteed that this value is always going to be rather large. Okay? So this is nice. What you can do is you can just set up a estimation block, right? And so you could just say like, okay, m hat is approximately, you could just say summation I equals 1 to n, right, where n is like the number of time steps, and it would just be x double dot I, your current measurement, ui delta t. So every time you get a new measurement, you just append to it and then divide by the same thing on the bottom, I equals 1 to n of xi double dot squared delta t. And so basically, if you had an m hat, if you let, say you were on the jth iteration, right? And you would say m hat is approximately summation of I equals 1 to j of xi double dot let's say jth iter, xi double dot ui delta t. I'm assuming the time steps are the same, divided by summation I equals 1 to j xi double dot ui, sorry, xi double dot squared ui. And then what you would do is you would save this. So this would be stored into memory, these two terms. You would just add the xjth measurement. So if you get a new measurement, you get the jth measurement, delta t, and add x double dot j uj delta t. And then what you do is you just keep adding these terms to the variable as the simulation is propagating forward. And essentially your errors are just going to kind of filter out, okay? I personally like this method. I think it's easier to understand. The book doesn't like it, okay? The book doesn't even show this method, okay? So I'm going to show you the way the book shows it, okay? So let me take a photo of this real quick. Package shipped. Okay, so what the book does is it says, I'm going to let p equal 1 over the integral from 0 to t final, x double dot squared dt. And I'm going to call this my estimation gain. Estimation gain, okay? If I take the derivative of p dot, okay, it's going to be, what, low d high minus high d low, and this is just the fundamental theorem of calculus, so you're just going to get x double dot squared all over low squared. So you're going to get 0 tf x double dot dt, which is basically just d dot of p inverse. What? Okay, for reasons beyond me, they want you to find the time derivative of p inverse. And so p inverse is the integral of 0 tf x double dot squared, okay, dt. And so the time derivative of p dot is just x double dot squared, okay? And we're going to save that in our back pocket. The other derivation, I'm not sure why I even did that. That book doesn't do it, okay? And then what you can do is if you write the estimation algorithm, so remember m hat is equal to the integral from 0 to tf x double dot u dt all over, is it times p? Did I do this wrong? Yeah, p is equal to that. Yeah, times p, right? This whole thing is times p. Well, here, let me just write it out. This is divided by integral 0 to tf x double dot squared dt, right? Which is integral 0 to tf x double dot u dt. And then 1 over this is p, so this is just p. And so that means that m hat times p inverse is the integral from 0 to tf x double dot u dt. And then what you can do is you can take a derivative, m hat dot, and you're going to get m hat dot p inverse plus m hat p inverse dot, which is found, is x double dot squared, equals, and then derivative of this with a time domain is just x double dot u. Okay? And then if you pull this to the other side, you're going to get m hat equals x double dot u minus m hat x double dot squared, and then whole thing times p, so m hat dot is p x double dot u minus p m hat x double dot squared, okay? And then factor out so E, what is E? So they defined a variable called E. Throw this marker away too. They define a variable called E, which is m hat x double dot, m hat x double dot minus u. And so if you look at this here, if we pull a minus sign out, we're going to get p m hat x double dot squared minus p x double dot u. And if I pull a p x double dot out, I'm going to get an m hat dot is negative p x double dot, and then I'm going to be left with a m hat x double dot minus a u, and that is E. And so m hat dot is just negative p x double dot E. And I know I just said earlier that the self-tuning controller gets rid of the derivative, but the model is still not there. There's no model reference controller. Okay, it's just E, which is your estimate times your measured accelerometer minus your control input. Multiply that by your accelerometer measurement again, times P, where P is this, where you integrate that over time using that summation algorithm that I was telling you before. Both of these will work just fine, any of these methods, okay? And so my control assignment for you is to choose a method, okay? You need to add, if you do this, so I guess let me write down the different methods, okay? Where's my phone? Okay, so let me show you the different methods. So method one for estimating m hat is you just do this. And guarantee that's not going to, this is going to work as long as your system is always accelerating, okay? If you use that and you're not moving, your estimate's going to blow up. The other thing is that when you are passing your accelerometer measurement through your sensor block, I want you to add noise with a let's just say a mean of 0 and a standard deviation. So I want you to add white noise to it. If you do this, your m hat's going to jump all over the place, and your control algorithm, again, mx double dot equals u, and u equals gamma v, m hat v, and v equals x double dot command minus kd x dot minus x dot command minus kp x minus x command. Okay, so this is your control law. If you use this, guaranteed this system's going to blow up. Okay. Method two is you do the filter idea, where you say m hat is integral from 0 to tf of x double dot u all over integral 0 to tf x double dot squared dt, and you estimate that on the fly. Okay, that's an option as well. Option 3 is you add m hat to your dynamics, and you do negative p x double dot e, where e is m hat x double dot minus u, and p is 1 over the integral from 0 to tf x double dot squared dt. And I'll go ahead and even add you a fourth method. Method number 4 is you take method 1, but you filter with a complementary filter. So you take m hat I plus 1 is, not sigma, alpha m hat I plus 1 minus alpha times ui over x double dot I. I don't think this is going to work because, again, if this blows up, you're screwed. So the reason why this is nice is because if you move and then stop, yes, maybe x double dot at the current time will go to 0, but the integral, like let's say this is x double dot as a function of time. Everywhere here, method 1 and 4 will work just fine, right? Because x double dot is not 0. When you get down to here, method 1 and 4 are going to die. They're not going to work. But these integral methods, because you're integrating the entire area, these will no longer update anymore, but they will at least converge to a certain value. Okay? So I would try, x command equals a constant and see what happens, and then x double dot x command is like, a sine wave. And I would try one of these methods and report back to me and tell me how they work. If I were to do one, I would do method number 2, because there's no dynamics. You just have to add the summations. That's my vote. Okay. Post in the comments if you have any questions, and I will see you next week.